By now we've learned how to describe the motion of objects moving in one dimension. But that's kind of boring. There are lots of objects in nature that don't move in just one dimension. There are, for example, planes that fly up into the sky. There are fish that swim around in the sea. There are bacteria that in your body that move in all sorts of crazy directions. And we want to be able to describe the motion of all of these objects. To do so, we will use these kinematic vectors, the position vector, the velocity vector, and the acceleration vector. Now, before we get into that, you do need to be at least conversant in using vectors. You might not have had a lot of practice in adding and subtracting vectors or decomposing vectors into their parts, but you need to be at least familiar with the idea of the unit vectors and how to add, subtract, and decompose vectors. So if you need to brush up or you're not familiar with these ideas, I've put at the bottom of this quiz links to 5 videos that describe all these concepts. And you can go and watch those videos. In fact, at this point, I would pause this video, go and watch those other 5 videos. They're pretty short. And then once you're familiar and with the ideas of manipulating vectors, then come back and finish watching this video. We want to be able to describe how an object moves through space. And of course, an object can move up and down, an object can move side to side, and an object can move in and out. Of course, I can't draw that because I'm constrained by using a flat screen. We'll talk more about this in class. You might imagine, though, that for each of these directions, we could draw the position versus time graph in that direction. So I could draw an x versus time graph, and maybe that one looks something like this. Maybe it's parabolic. And I could draw a y versus time graph, and maybe that one looks something like that. And of course, I could draw a z versus time graph, and perhaps it looks something like that. So each one of these graphs now describes how my position in that direction changes with time. And each of these would yield then a function. This would be the function of x as x changes with time. This would be the y function as it changes with time. And this one would be the z function as it changes with time. However, the thing to remember is these, the way we've written them, these are scalar functions, but these really aren't scalars, right? These are positions. They have direction. And so what we need to do is we need to remind ourselves that these are vectors. And so we do that by using the unit vectors. So this isn't just x of t, this is x of t I hat. The I hat is the unit vector in the x direction. Now I'm using I hat, j hat, and k hat as my unit vectors. There are lots of different ways that different books will represent unit vectors. I'm using the ones that your book uses. Now this tells me I'm not just a scalar function, but I'm actually a vector function. I'm the vector of x as it changes in the x direction. Of course, then we have, for these other two, j hat and k hat. And now I have 3 vectors. I have how my position x changes in the x direction with time, how my position y changes in the y direction with time, and how my position z changes in the z direction with time. When I add those all together, I get a new vector that is my position vector, and we use the letter R to denote it. Now don't ask me why we use R. There's only 26 letters in the alphabet plus whatever we can steal from the Greek. But the R now denotes my position in time, and it is a vector. It tells me how my position changes in all three directions with time. So once we have the position vector, we can now describe the displacement vector and the distance. Remember, distance is not a vector, it's a scalar. The displacement vector, however, instead of being delta x, becomes delta r. And that is just then my r vector at some later time minus my position vector at some earlier time. That gives me my displacement. So if, for example, I had, let's say, r of my later time was 2 I hat plus 3 j hat minus 4 k hat, then I had my earlier time position was 2 I hat plus 2 j hat plus 2 k hat. Now I could find my earlier time. Sorry. Now I could find my displacement vector. I would just say, all right, well, this is going to be 2 minus 2 I hat plus 3 minus 2 j hat plus minus 4 minus 2 k hat. Sorry, I'm running into things. Or in other words, this is 0 I hat plus 1 j hat minus 6 k hat. And I can immediately see that I mostly moved in the z direction. The distance now is then just the magnitude of my displacement vector as it was before. So in order to find out what my distance is, I would have to use the Pythagorean theorem, and I would take whatever my x component was, square it, add it to my y component squared, and my z component squared. All right, so in this case, I would get square root of 0 squared plus 1 squared plus minus 6 squared. Right, remember that I would square the minus. Then I would end up with a distance of, let's see, 6 squared is 36. So square root of 37. That would be my distance for this vector. Right? So we now have the three different quantities. We can talk about the position vector. We can talk about the displacement vector. Or we can talk about the distance. Now, I call this the distance. However, it's more correct to say that this is the magnitude of the displacement. But if my step size in time is small, if they're really close together, then this is the distance for that step. And if I just go back to my definition and add up all my little step sizes, so if I take all my little steps and add up all of their little magnitudes, then I would get my total distance. So calling this a distance is maybe a little bit confusing. Let's not. Instead, I will try and be more careful and call this the magnitude of the displacement, which is more appropriate. You know from our discussion of velocity in one dimension that the velocity is the derivative of the position with respect to time. But now we know that we actually don't just have position in one dimension, we have position in multiple dimensions. And so if we want to find our velocity vector, we now need to take our derivative in each of those dimensions. So we would now have a velocity in x, we would have a velocity in y, and we would have a velocity in z. And each of these is a component of my velocity vector. So to find my velocity in component in y direction, I would just take my derivative of my y position of my the y component of my position vector with respect to time. And to find my velocity in z, or the z component of my velocity vector, I would take the derivative of the z component of my position vector with respect to time. So all of these now, these are the components of my velocity vector. And to get my velocity vector, all I need to do is then add these up. So my velocity, full velocity vector, well, that's just my x component. But of course it's a vector, so I'm going to write I hat plus my y component, j hat, plus my z component, k hat. This would give me my velocity at any instant in time. If instead of an instantaneous velocity, I want to find an average velocity, well, I already know how to do that too, right? My average velocity before was just the displacement divided by my change in time. Now we know that for our displacement, to find my displacement vector, I'm going to take my r, my position vector, at some later time, minus my position vector at some earlier time, right? That's my displacement vector. So if I just do that and then divide by my interval of time between those 2 points, this would now give me my average velocity. So I can get my instantaneous velocity, or I can get my average velocity. And either one I will get from my position vector. And everything that we see, it's just an extension into 2 and 3 dimensions of what you learned in 1 dimension. So in 1 dimension, we learned how to take a derivative of a function. Now we just have to take 3 derivatives, 1 for each function. In 1 dimension, we learned how to take the difference of 2 positions. Now we just have to take the difference of 2 position vectors to find the displacement. Since you now know that 2 and 3 dimensions don't really add much new. The physics is all the same. The only thing we've added is now you have to do everything 3 times. You might already guess what the acceleration vector will look like. In one dimension, we learned that my acceleration was the derivative of my velocity with respect to time. Now in 2 or 3 dimensions, I just have components of my acceleration are the derivatives of the components of my velocity. So I will have a component of my acceleration in x, or in the x direction. I will have a component of my acceleration in the y direction and a component of my acceleration in the z direction. And this will just be the derivative of my velocity with respect to time in the y direction, and the derivative of my velocity with respect to time in the z direction. Of course, these different components could be functions of time themselves, could be dependent on time or not, so we'll include that in our equation. But now, of course, we have the components, and to get the full vector, we just take them and we add them up. So my acceleration vector, that's just going to be my x component in the x direction, so I hat, plus my y component in the y direction, so j hat, plus the z component in the z direction, so k hat. And there is now my acceleration vector. Now, if you really want to impress people, you can write this a slightly different way, right? We know that our velocities are derivatives of position, and our acceleration is derivative of velocity. So when you get further in calculus, you'll learn about the second derivative, and we can write each of these components then as the second derivative of our position with respect to time. Now, why is this important? Well, this is called curvature, and when you've studied a little bit more in your calculus, you'll understand why that is. It deals with whether your function is curving up or curving down, but for our part, it's just a way to impress your friends. So we now have our acceleration vector, our velocity vector, and our position vector. Of course, we could also calculate what our average acceleration was, and you could probably at this point guess what it would be. This is going to be, I'm running out of room, my apologies, just the difference in my velocity vector now at some later time minus my velocity vector at some earlier time over the interval of time, right? Where each of these vectors now involve the x, y, and z directions. Now, at this point, you might justifiably ask, why would we do this? Why would we double or triple the amount of work we have to do? And the reason is, in fact, the reason why vectors were invented and why they came about is an interesting thing happens when we look at motion in 2 or 3 dimensions. Let's just, for the moment, restrict ourselves to 2 dimensions, because I can draw that. If we were to look at an object that moved in 2 dimensions, so say the x dimension and the y dimension. Let's say I have a ball, and I throw it into the air so that it follows this kind of trajectory. If I were to draw you the motion diagram of these directions independently, let's say in the x direction. In the x direction, I would find that I get a motion diagram that looks something like this. And at this point, you should recognize this as a constant velocity diagram. Whereas in the vertical direction, so in my y direction, what I would see is a motion diagram that looks something like this. At least that's what it would look like going up. Going down, of course, it ends up looking like that. So this is my upward motion, and this is my downward motion as the ball flies up and down and falls down. And this you should recognize by now, hopefully, as constant acceleration. That's a constant acceleration motion diagram. And so interestingly enough, the motion in these 2 directions is independent. So these directions that are perpendicular are independent in their motion. So whatever happens in x is independent of y. And whatever happens in y is independent of x. And the only thing that gets shared between them is time. And this independence of motion is very powerful. Let's suppose I have this vector. Once I've found my y component and my z component, or sorry, my x component, what that means is now I can write down my kinematic equations for my x direction, and I can write down my kinematic equations for my y direction. And I never have to worry that I might somewhere get an equation that involves both x and y. I will never get this. They stay independent. So all of my equations remain separate. I'll have an equation for the velocity in the x component involving the x component of the acceleration. I will have an equation for the y component that only involves y components of the velocity and the acceleration. And I never will get crosstalk. I'll never have y's appearing in my equations for x's, and I'll never have my x's appearing in equations for y's. This is extremely powerful. And then, of course, the only thing that does carry across is my time. My time variable will bridge between the two. So I can now write down known quantities in the y direction and known quantities in the x direction. Try and write out my equations in the x direction and in the y direction, and solve a little bit in one dimension, solve a little bit in the other dimension, maybe solve and try and find time, and that'll let me bridge back and forth. And so this is how we will go about solving these different kinematic equations in multiple dimensions. We'll start in one dimension where we'll have a lot of information. We'll usually try and find time. Time will be our key that will let us move to the other dimension where we'll begin to be able to solve equations in the other dimension. At this point, you're ready to extend your knowledge of kinematics into 2 and 3 dimensions. You now know how to use the position vector. You now can turn that into a velocity vector, and you can calculate the acceleration vector. And you know how to calculate the displacement vector and turn that into a distance measurement that you can use. Of course, there are lots of problems that we can now answer, lots of interesting questions we can address using this. Your book goes through several examples. The class of problem that we'll talk about next, which is projectile motion, that is a special class. Not everything in every moving object is a projectile. But there is a special class of moving object that we call projectile motion that is very interesting. And so we'll talk about that. That'll get its own subject. But now you're all ready. You know everything you need to know to begin to use kinematics in 1, 2, or 3 dimensions.